So hello YouTube, this is gonna be my second video. This is not gonna be a homework session. It's gonna be studying. I'm gonna go to my school's portal for content portal, and we're gonna go through some stuff, and then I'll see if I can find some YouTube videos. And that'll be that. Actually, you know what I kinda want to do here? This is much better. Oh. In the chapter, you'll learn how the ideas displacing an average velocity help us describe straight line motion. Placing average velocity. So I like to put this stuff in. So here's what I'm gonna do. I'm gonna read these learning outcomes instead of caring about them being learning outcomes. I'm going to just write questions. Oh my god, dude. You know what? Oh. Dude, why is it not resizing? What is going on right now? This is so unprofessional. The meaning of instantaneous velocity, the difference between velocity and speed. The meaning of instantaneous velocity. How to use average acceleration and instantaneous velocity to describe change in velocity. What is the relationship of instantaneous velocity and acceleration? That's a good question. How to solve problems with which an object is falling freely under the influence of gravity alone. How to solve problems in which an object is falling freely under the influence of gravity alone. Isolated gravity problem sounds like pretty similar to what that's saying. How to analyze straight line motion when the acceleration is not constant. How should one analyze? Okay, introduction. Kinematics. Kinematics is the study of motion. So we're gonna do what I learned how to do in my Spanish lessons. There's some interweaving context here. I just learned that in like metacognition class. Interleaving concepts. Let's go. So what I'm gonna do is I'm gonna read through about 5 slides, and I'm not gonna try to write anything down. I'm just gonna accept the ambiguity of what I'm dealing with and what I don't understand, and I'm just gonna keep reading, and my brain will pick up on patterns. Hopefully. Kinematics is the study of motion. Velocity and acceleration are important physical qualities. A typical runner gains speed gradually during the course of a sprinting foot race and then slows down after crossing the finish line. Okay. So that's a change in acceleration there. Position and coordinate systems. To specify position, we need a reference point, the origin, a distance from the origin, and a direction from the origin. The post office defines a position and origin of a car in relation to a post office and a cow. The combination of an origin and an axis marked in both positive and negative directions makes a coordinate system. So this is like so the definition of a coordinate system is just a system with some kind of axis from a reference point, a center reference point, or some reference point. So like you could make a coordinate system based off of dots. Well, that's it. Let's see. So technically a coordinate system could look like this. Let me move this thing out the way. Oh my god. Ah! Stop it. Move this thing out the way. It could look like this. Meow. That's a goofy coordinate system. That's why I made the goofy sounds. You guys heard that? Okay, no. So the origin here is this dot point, and you can reference the curls. Am I going this curl, this curl? I'm in between the first two curls. I'm right here. Curl. Something weird. It's just saying it needs an origin and some sort of axis and reference. Position coordinate system. The symbol that represents positions along an axis is called a coordinate. X or Y. This is the symbol coordinate. Start the race natural choice for the origin. Positive values of x extend to the right. The units in which x is measured go here. A change in position is called displacement. A displacement is a change. So this is Sam's displacement. His x final. So displacement formula for displacement equals final, and then axis or whatever you're measuring against minus units minus initial axis units. So the reason I did it like this, it's like really weird. I don't think I've seen any of my teachers actually write it like this, but I just kept it stupid simple. So I said the axis because it's defining what axis you're moving about or you're comparing your movement to, and you want to make sure these are like pretty much the same. And your units, what amount multiplied by multiplied by some unit to actually get a valid distance in the real world that you can understand. So yeah. And this is just showing x final minus x initial, and your final is your endpoint. Displacement is the difference between a final position and an initial position. Distance versus displacement. Distance is defined as a length of a path. Displacement, delta x, is defined as the change in an object's position. This must include the direction in which the object's position changed. So like delta x, x final minus x initial. SI units for both distance and displacements is 1 meter. The particle model. Let's go. The particle model is of motion is a simplification in which we treat a moving object as if all its mass were concentrated into a single point. Motion diagram and displacement average velocity, difference between velocity and speed. Relationship. How should one approach so this could be one of the questions that we had earlier. How should one analyze changing acceleration, straight line motion? We could say, I think the answer for this might be a particle model displaying the change in acceleration in a simple way that can be easily understood and recorded later. I should probably change the that might be it, I don't know, but that makes sense if those are connected, I feel. Wow, I can't just change this one part. Oh, yeah. Well, too bad. That's fine. That's fine. I'll just do this then. I gotta move this. Alright. Two runners jog along a track. The positions are shown at one's intervals. Which runner is moving faster? I want to say A is moving faster because there's more space in between the dots. No. Two runners. That vision is showing which runners moving faster. This is 5. This is 10. I thought about that too much. The positions are shown at one's interval, which running is moving faster. Two runners jog along a track. Two runners jog along a track. The times at each position are shown, which runners move faster. I want to say they're running at like the same speed. Because, well, they're kind of perfectly aligned. Like this guy just has a constant slow space, and this guy's like jumping. I don't know what he's doing. He might just have a longer stride, bro. I don't know what's going on. In order to quantify motion, we need to consider changes in time, which we call time intervals. Oops. In order to quantify motion, we need to consider changes in time, which we call time intervals. We use position time intervals. What do we use to quantify motion with changes in time? Time intervals. A time interval of delta t measures the elapsed time as an object moves from an initial position of xi at the time to ti at time ti to a final position xf at the time tf. Time is always positive unless you go back into the future. But even if you do go back into the future, time is still positive relative to the observer, right? Because you got a guy that's going back into the future, but his life is still his life, so he's looking at himself like, "Whoa, I was a kid, and I'm here. I made it, so I can go back into the future." All right, two runners jog along a track. The times that each position are shown faster. Maria is at a positive x 23 meters. At a position x equals 23 meters, she then undergoes a displacement. What is her final position? Interesting. Yeah, I see a delta there. I see a 5. Uh, it's gonna add or subtract 5. I see a 5, right? So let's say it's something. It's 70 something, or it's negative. Ooh. It's negative something. I think it's A or D. An ant zigzags back and forth on a picnic table as shown. Bloop, bloop, blop. The ant's distance traveled and displacement are distance traveled. It said distance traveled is the. Oh, okay. And it zigzags back and forth on the picnic table as shown. The distance traveled. 10. Wouldn't this be this whole thing 50? And the displacement is 40 to 10, which is like negative 30. Or is displacement just 30? I think it's negative 30. Motion at a constant speed in a straight line is called uniform motion. Boy. Motion at a constant speed in a straight line is called uniform motion. What is constant motion at a constant speed in a straight line called? You know what else I'm about to do here? Questions? Probably should have put questions up there too. Okay, I'm about to organize this a little better. What I'm gonna do? This one, I'm gonna put the questions like to the side. Or no. A weird little coordinate thing here. Move that to the side. Okay. Oh. Uniform motion. So uniform motion is a constant speed in a straight line. During each second, the car moves twice as far as the bicycle hits the car moving at a greater speed. Speed is distance traveled in a given time interval. So this is why speed, even though we're not talking about this right now, this is why speed is a vector. So it says speed equals distance traveled in a given time interval. And it says speed is equals to distance traveled in a given time interval divided by time interval. So if you break this down, how like the SI units, the Systems Internationales de Uni System International de Uni. If you break it down like that, you get speed. One, we're talking about what I said before though. Speed is a vector because a vector is something that has a magnitude and direction. You see here that speed has a distance traveled over the elapsed time period, and it has the elapsed time period, which is a direction. Now, just because something always goes in the same direction doesn't mean it's not a direction. Just because time is always going in the positive direction. That's something that I know I didn't have to explain, but that's something that kind of like I was confused about for a second. The vector has magnitude direction. Also, if you like break it down into like speed equals a length divided by time, which are both, and in Systems International, this would be a meter divided by a second. This is the standard for speed. Meter divided by a second. Now I think I'm trying to read it earlier in the British system, the imperial system. Imperial, it would be like a feet over a second, a foot over a second, something weird like that. Speed measures only how fast an object moves. Velocity tells us both an object's speed and its direction. Velocity. Okay, so I might have been. I've been learning that like speed is almost interchangeable with velocity. I'm getting caught off guard here, because that is what we've been doing in class. But let's you know. So speed is only how fast an object moves. Velocity tells us both an object's speed and its direction. Okay. Oh, okay. That makes a lot of sense. Okay, that makes a lot of sense. So speed can't be negative. Okay, that makes a lot of sense. That makes a lot of sense. That's what that means. Speed can't be negative because it's like it's just, so whether you're going north or south, if you're going 50 miles an hour, your speed is 50 miles an hour, right? But velocity would tell you whether you're going positive or negative 50 based on the delta y in this equation here. So that's the difference. Even though they're basically the same still, but velocity can be negative. Looks like, I think. So this is the interval. Delta x, delta y. Wish I had more symbols. I could probably install like a pack or something for math. Or I can just do this. All right, displacement time and average velocity. This is gonna get back into, let's take a quick little, go back real quick. Oh crap, where'd it go? Placing, okay, this is where we're gonna answer the first question. How does displacement average velocity help describe motion along a line? A particle moving along the x-axis has an x-coordinate. The change in the particle's coordinate is delta x, which is the x2 minus x sub 2 minus x sub 1, which is x sub f final minus x sub I initial. The average x velocity of the particle is v sub av minus x, which is equal to the delta x over the change in t in time. So it's just saying average velocity, no matter how much the velocity changed, this would give you a standard pace of how fast he was going within that time period. So that's how it would help describe the motion along the line. So displacement over the change in time within a certain interval gives you the general velocity or how fast something was going within that interval, regardless. No, not regardless, but like it's useful for generalizing when there's been many changes in velocity. I would say that is pretty decent. It's a pretty decent explanation. The average x velocity of the particle is this. So that's another thing I like to do. I might be able to start doing this in my own math notes, but if we break this down here, now I can copy this later and start doing this. So So I think when you are using a variable with subscripts to describe a process, you can use subscripts to add detail. Here, A equals average V equals velocity, and X explains which axis this is on. Cool, because I can start using these in my notes. Because I know my math teacher last semester used a bunch of subscripts, and I just ignored them all the time. I got a decent grade in the class, but I'm like, bro, if I can level up a small thing in the way I write my math, that would give me a lot more understanding later. The average x velocity of straight particle motion line, motion during the time interval t1 and t2. So yeah, these deltas, I'm reiterating, it just means change. So this is the x final minus x initial. This is time final minus time initial, and then it's basically showing you that here. This, and if you look at it like a direction and a magnitude of some sort, this is basically just the same formula for rise or run if you do remember it for a slope. So you could easily like graph velocity as a slope. Final time minus initial time, x component of the product of displacement, time interval. Rules for x time velocity. So this is just telling you how you look at a chart. So if we just copy this real quick. I'm about to just copy this and like draw a chart. And we're gonna look at the rules. And we're gonna draw ourselves a little velocity quick. So this is this is the positive x, this is the positive y, negative x. It says positive and increasing. If the x coordinate is positive and increasing, getting more positive, the particle is moving in the x direction. It's getting positive, it's going this way. Positive and decreasing, getting less positive, the particle is moving in the negative x direction. It's just telling you that, like, if you started from positive, like right here, and you're going smaller, you go over here, you're going in the negative direction. Okay, and it continues with these. Average velocity. The winner of the 50 millimeter spray is the winner. The winner of the 50-meter swimming race is the summer. The winner of the 50-meter swimming race is the swimmer whose average velocity has the greatest magnitude. So this is just saying, like, if you did, a time. It's basically saying whoever gets the, well, you know what it means. Whoever gets the shortest amount of time, because velocity is displacement over a time interval. So if a swimmer has a constant, each swimmer has a constant for the displacement, then they want a smaller and smaller time. Representing position. Every dot is in the motion diagram below represents the student's position at a particular time. The dots show the student's positions at all times in the table. Cool. The graph shows the student's motion as the graph of x versus t. From position to velocity. What are those other questions? What's it from? Okay. Ooh, okay. We forgot. So let's go back before we keep going. Let's try to see if we can answer any of the questions about what we just read. Remember, we didn't stop too much. I tried to like talk through some stuff, but we didn't really stop. What is the difference between velocity and speed? We actually did go over this. Speed is the absolute speed is the absolute magnitude of the ratio of displacement or change along some axis divided by change in time, while velocity is the positive. Oh God, hold up. Let me see if I can fix this real quick. Oh, velocity is the positive or negative direction of that same ratio. At least that's how I interpreted it. How does displacement and average velocity help describe emotional? I already answered that. I'm about to kind of delete this real quick. Oops. How will you describe? We haven't done that yet. What is the relationship between instantaneous velocity and acceleration? How should one approach isolated gravity problems? How should one analyze a chain acceleration, straight line motion? How should one analyze changing? I think I already said that for using a particle. I'm just gonna write that. Actually, like a simple answer real quick. Using a particle model. No, motion. Is it a motion diagram? A motion diagram. It's like simple, but I can answer it and I can elaborate later. But at least I have an answer, you know. A particle model displaying the change in acceleration in a simple way that can be easily understood. Oh, I already had an answer. Great. That's dope. And and this stuff. Who would have thunk? Who would have thunk it? So right now we're looking for instantaneous velocity problems in isolated gravity. That's top of mind. We're gonna try to see if we can remind ourselves about this as well. What do we use to quantify motion with changes in time? Time intervals. What is motion at a constant speed in a straight line called? Uniform motion. Okay. All right, from position velocity. On a position versus time graph, a faster speed corresponds to a steeper slope. We did that earlier, but I don't like how they're doing us like that, bro. Like, what's up with you? Oh, what do they know? Okay. Let me see if... No. Slope of graph run. That's weird, man. Position time graph. Position time graph. For a displacement along an x-axis in objects x average x velocity average x of the velocity equals the slope of a line connecting the corresponding points of the graph position x versus time. So what's cool about this is this was exactly what we said earlier. What we're gonna do is I'm going to snapshot that and put that next to what we did earlier. Our explanation. How to displace an average velocity help describe motion along a line. This is a perfect connector for that. I'm displacing over change time with a certain interval. Yep. That's a good explanation. That's a good simple explanation. From position to velocity. Okay. Here's a motion diagram of a car moving straight line road. So it was at a stop, probably, or it was like it was like turning, or oh crap. Here's the motion diagram of a car moving along a straight road. So because we're which velocity versus time graph matches this motion diagram? Velocity versus time. Which one is velocity? This is velocity. So first it was like going really up, and then it was going slower, but still moving. Oh no! It was going slower, but then it was moving faster. Which one models this? I want to say this, but this is 0. C? Or I'm thinking A or C. I don't know why. But wouldn't like this be the actual speed or velocity diagram? The this would be the actual like position, and this would be the velocity. C. Okay. But this one right here, I think would be the position one. Here's the motion diagram of a car moving along a straight line road. Straight line road. I had some flashbacks there. Here's a motion diagram of a car moving along a straight road. Which velocity versus time graph matches this motion diagram? So it's going to the left. He's going this way. It doesn't matter which way he's going, right? He's going slow, then fast. There's a bunch of them that's going slow and fast, but it's on the right of 0. D? No! D? He's going slow and fast. Or is it fast? This one got me. Slow. Then fast. But it's the opposite direction though. And velocity does matter about the direction. Because this is X. And X is going down. Oh, X is going down. Bro, I'm tripping. And this is X. D. That makes sense. You know why these things bug me out? Because I'm just not used to X being on this line. And this is a good way to understand like the tools we use even more. Because these always just weird me out, dude. I like Y being here. I like X being here or something else being here. Shouldn't matter. But X being here just weirds me out on this axis, on the vertical axis. But that makes sense. I get it now. The instantaneous velocity, here we go. This is our moment of truth. This is where we find our questions at. The instantaneous velocity at the specific instant time or specific point along the path and is given by Vx. I'm actually going to stop here, not the video, but I'm going to stop here. And I'm going to go into, my computer's getting slow. And I'm going to go into depth about what I see right now. So one thing about these D's here is that we know that V is on the x-axis. That's the velocity. And we know the subscript is a description of which axis or a description of this variable. So we know V is on the x-axis, or where you're going to put it, equals dx over dt. Now, we know that the velocity is some change over a period of time, and we usually see a delta here. Isn't that weird? We don't see a delta here right now. Why are they giving us this weird D and not delta? Is what I'm asking myself. And this D is, let's see if I can remember the name. See if I can remember the name, guys. It's a infinitely small piece or infinitely small change. It's called a derivative. No. Let's see. I'm about to check. We're about to look it up, guys. What's a what's a chud? What's a good word for infinitely small change starts with a D in math. Differential, that's what this is. This is differential. And what this differential basically is just a super tiny rise of a run. It's like it's like you get a slope and you go way zooming in, like as far as you can zoom in on that line. The rise of a run infinitely small. That's what that D means. That's why they didn't use delta here, because they're talking about rise of a run at an infinitely small point, and it's so small that it's basically instantaneous. Um, the average speed is not the magnitude of the average velocity. The average speed is not the magnitude of the average velocity. Okay. The magnitude of the average velocity would still be a straight line, so that would be like that makes sense because this would have a direction. I'm trying to figure out. Instantaneous x velocity, the average speed. I'm really trying to think about this though. I really think it has something to do with like the average velocity having a direction and negative positive. I mean, technically, can the magnitude of the average velocity and the average speed be the same if the velocity maintains like no, that literally would just be speed. It would be uniform motion. I guess that's so true though. That's what we just did. From delta t to 0, lambda delta t to 0 equals instantaneous velocity, x velocity of a particle motion. I'm gonna copy this and see if I can like. So it's in the limit from delta t to 0, which is the displacement of time all the way to 0. Delta x over delta t equals dx dt. Oh, I see. It's saying because like it's becoming infinitely small, so it's basically approaching 0. That's how you get the differential x over differential t, because of delta time going to 0, approaching 0 with your delta x over delta t. You'd get like, so say like you're a guy and you know that this slope is something, right? You zoom in and you're like boom, 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 boom. You zoom in and you're like, oh my god, I want to know the slope instantly. So you zoom all the way so far in that you go like this. And you make another tiny little slope here. That's an instantaneous slope, but way even smaller than that. It's like a Mandelbrot slope. You know what I'm saying? That's what that is. That's why it's instant. Finding velocity on an xt graph. Find velocity on an xt graph. Velocity. Slope 0, v x equals 0. Oh. Particles is at x is less than 0, moving in the x to plus x direction. Mm. 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 Average acceleration describes the rate of change of velocity with the time. Average acceleration. Acceleration describes the rate of change of velocity with time. The average x acceleration is a. So acceleration is how fast you're changing speeds, basically. So if you have a speed here, I know speed and velocity are different, but we're just making it easier on ourselves. Okay, if you have a velocity here, say you're going like, you ever seen those like people that brag their car can go to 0 to 60 in 5 seconds? So if the time is small enough or big enough, and the velocity has a large enough displacement, that's when that becomes impressive. That's where accelerate. That's what acceleration is. Like, bro, I can go 0 to 60 in 3 seconds. Bro's driving a Lamborghini. You know what I'm talking about? Um, um, and this is just the subscripts. We can reiterate for myself and others. The subscript is a descriptor of this variable here, and I don't know why you have to put the same variable descriptor again when you're doing it in the subscript, but that's a thing. It's just your acceleration, um, change velocity, acceleration velocity over x on the x-axis. Average velocity. I'm tripping. Acceleration, average velocity. Is a descriptor that says acceleration is your average velocity and it's showing that it's going along the x-axis. Graphical interpretation of average acceleration. The motion diagram shows. Now I'm about to just keep on reading them, keep on blitzing. Actually, I'm about to write some quick questions too for later. What is the formula for acceleration, and how does acceleration is acceleration related to velocity? Velocity. Um, what is the use case of instantaneous slope? Let me zoom out real quick because I just realized that we went over some stuff that we were supposed to check up on. How would you describe instantaneous velocity? Let's see, how would I best describe instantaneous velocity? I would say at a very specific, at a specific point long in time respects to some axis says ratio some displacement of position over time. The rate of that was super sloppy, but I feel like it was decent. I don't know, but how would you describe instantaneous velocity at a specific point in time in respect to some displacement of position over displacement in time? The exact change as close to zero as possible. What is the relationship between instantaneous velocity and acceleration? Oh, acceleration acceleration is the change in velocity over time to get the acceleration at a point, it would be the ratio of instant velocity over the differential displacement in time. How should you solve gravity problems? You didn't tell me. I don't know. I don't know. How would I know, buddy? What is the formula for questions? What are your questions? What are your questions? Average. Okay, we're down, 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 down. Figure is just instantaneous. Again, motion diagrams. Past this, past this, past this. Okay. Oh no. Not a word problem. I thought I was just gonna be taking notes. All right, let's go. I got this. I ain't scared, bro. Fuck, I'm a grown man. All right, you drive a beat up pickup truck along a straight road for 8.4 kilometers at 70 miles an hour. So, 8.4 8.4 kilometers at 70 kilometers an hour, at which point the truck runs out of gasoline and stops. Over the next 30 minutes, you walk another 2 kilometers farther along the road to a gasoline station. What is your overall displacement from the beginning of your drive to your arrival at the station? Well, one, that first question, the speed or velocity doesn't even matter. Let's get that out the way because you're asking me about my overall displacement. So obviously, I went 8.4 kilometers. Okay, and then I walked 2, so that's 10.4 kilometers. That's my displacement. You drive a beat up pickup truck on a straight road for at which point the truck runs out of gasoline and stops. Over the next 30 minutes, you walk another 2 kilometers along the road to a gasoline station. What is your overall displacement? Assume for convenience that you move into the positive direction of the x-axis from a first position of x1, 0 to second, x2, 8.4 to 10.4, then displacement delta x1 bond. Boom. All right. What is the time interval delta t from the beginning of your drive to the arrival of the station? That's where this comes in, baby. The time interval. So first of all, we were given our givens here. We got 30 minutes. That's we know that's 30 minutes. Then all we gotta do is take out the time here. So we got 70 kilometers over 1 hour. And we traveled 8.4 kilometers. $8.4 kilometers. Actually, you know what I'm gonna do? Oops, did not mean to do that. You know what I'm gonna do? Actually, I'm gonna do 1 hour because this is this is. Am I bugging here? Am I bugging? Should I just? Am I tweaking right now, bro? This is why I just did uniconversions and they went smoothly. Now I'm like, oh my god, what am I doing? Is it the same? What am I doing? Do you know? Boop, boop. 8.470 divided by 8.4. 70 divided by 8.33. Nah, I think you gotta reverse it, gang. 1 hour. Yeah, I think I had it right the first time. I think either way it doesn't really matter, but divided by 70. And that's 0.12, 0.12 an hour. If you convert an hour to minutes, 60 times 0.02012. 60 minutes times 0.012 is 7.2. So like you got like 37.2 minutes. That's probably wrong. Oh, did they say they wanted it in hours? I don't think I did it wrong actually. Beginning your drive to the right of the station. Okay. Suppose to pump the gasoline, pay for it. Average speed. You'd have to do 0 there. Oh, I see. Guys, I'm getting sleepy. I gotta get. I'm trying to get. I'm trying to hit hour 30 in these videos. I got 15 minutes left, and I'm gonna pause and then make another video. After that, probably gonna get to 89. Actually, I'll probably go back to these questions. I'll probably stop here because I'm not even here right now. I'm not even doing it. Um, let's see if we remember this. The formula for acceleration is the velocity over some axis, subscript of that axis divided by time, which is just if you did like the systems to unit, it would be the length divided by time squared, and then what is the use case of what is the use case of instantaneous slope? We actually went over this. I forgot where I wrote it. I think I accidentally deleted it. But you could get exactly what the velocity or some other metric was depending on your current dimension, um, or depending on your current like derivation. Actually, that's not the word I want to use. Something except like depending on your dimensions, like I said before, you could use instantaneous slope to get the exact change at that very specific point. All right, so I'm gonna stop this video. I'm on page 52. And then hopefully like next upload, I have 2 uploads that I messed up because I deleted the video right after I finished. So if you see this or it's on my page, just know I didn't mess up and I got it up there. So we're gonna start from page 52 on the next one, and then we're gonna go to the next week's. We're gonna pre-study for next week, and then we're gonna do some history, and then I want to do some. I really do want to do some Spanish on my channel. I actually did record my tutor me and my tutor, but I accidentally deleted that too. I keep it's like a like just one flip click and it's gone. So yeah, so that's the plan. Thank you.